Hey, what's up guys? Welcome to the second video of this mini sub-lesson on induction, where today we'll be taking a look at one type of induction problem that commonly exists on IB's paper 1 exam. So we'll be examining the question that asks us to prove that a function, I don't know, let's just call it f of n, is equal to some given expression. So for instance, an example of such a type of question is like the proof that we just did in our last video, where we proved that the sum of the first n integers is n times n plus 1 over 2, which is of course an expression. So there are 3 tips that will make solving these types of problems a lot easier with just a bit of practice. All right. So tip 1 is that when you do your inductive step, you want to write the expression you get from your inductive step in terms of the expression that you get from your inductive hypothesis. Okay, so you want to get from your inductive step, I'll just call it IS, in terms of the expression from your inductive hypothesis. And these two expressions are the ones that you get from plugging in n is equal to k and n is equal to k plus 1 in your given equation. All right, so what this does is it allows you to use the assumption that you made in your inductive hypothesis. And if you're a bit confused, that's okay. I'll explain how this tip works in our example. So step 2, or tip 2 rather, is that you want to always figure out what is happening when you're going from n is equal to k to n is equal to k plus 1. Okay? So figure out what is really happening when you go from n is equal to k to n is equal to k plus 1. What does this tip mean? Well, it's just essentially saying that you're going to get 2 equations, one from your inductive step and one from your inductive hypothesis. And these 2 equations will look fairly similar. However, there's going to be a critical difference between those 2, and you want to find out what that is. So are you adding an extra term? Are you subtracting a term? Maybe you're multiplying, maybe you're dividing, maybe you're raising your expression to a higher power, maybe you're differentiating an extra time. But make sure you figure out what is really going on when you go in between your inductive hypothesis to your inductive step. Okay, so tip 3, and this is less of a tip than it is of a general piece of advice, is that you make sure you always do your base case and your inductive hypothesis. All right, so always do base case and inductive hypothesis. I'm going to put 3 exclamation marks here. This is really important, and you should do this even if you can't figure out the rest of your proof. I've already mentioned this before, and I apologize for the repetition, but it's just such an easy way to get free marks, and as you guys know, every mark on the IB exam matters. So that being said, let's do an actual example that we can practice. So that we can practice these 3 tips in action. All right, so this problem is taken from the 2015 IB Higher Level Mathematics Paper 1 times 1 exam, if you guys are curious, whereby they give us a function. We're going to call it f of x. We're going to call it y of x, and that's simply defined as x times e to the 3x. And then basically it's asking us to prove by induction the following statements. All right, so it's asking us to prove that the y-th derivative, not n plus 1, it's just n. The y-th derivative, the nth derivative of y with respect to x is equal to the expression n times 3 to the n minus 1 times e to the 3x plus x times 3 to the n times e to the 3x, where n is a positive integer, and x and y are any real numbers. All right. Cool. So first things first, we're going to apply the third tip and do the base case and the inductive hypothesis. And one thing I forgot to mention, sorry about that, is that you want to do these tips in ascending order. So you want to, whenever you do your induction, you want to start at the bottom and work your way to the top. So let's do our base case first. And one thing to note is that we're doing base case, we're doing induction on the variable n, right? Not x or y, which means that we're going to manipulate n, not x or y. That just means that we're going to plug in n is equal to 1 in our equation, as n's domain is the positive integers, and 1 is the smallest positive integer. Plugging n into this equation up here gives the equation dy over dx is equal to, plugging in 1 gives 1 times 3 to the 1 minus 1, which is just 1, of course. So we're just left with e to the 3x, and then we're adding x times 3 to the 1 is just 3x times e to the 3x. So how do we prove that this little equation here is true? Well, we know that y of x is equal to x times e to the 3x, so we can just substitute that in on the left-hand side, here where there's a y. So doing that, the left-hand side simply becomes d of x times e to the 3x, d over dy of, sorry, not d over dy, d over dx. d over dx of x times e to the 3x. And of course, this is just a derivative of x times 3 to the 3x with respect to x. So how do we do the derivative of this? Well, we can use the product rule, right? The product rule states that if you're trying to find the derivative of a times b, what you do is you take the derivative of a, you multiply it by b, then you take the derivative of b, then you multiply it by a. And what we can do is we can say let a is equal to x, let b is equal to e to the 3x. Differentiating both, we get the derivative of a is 1, of course, and the derivative of b is nothing but 3 times e to the 3x. And if you don't know how we got from this step to this step, we just simply applied the chain rule by making the substitution u is equal to 3x. So therefore, we've just done the chain rule. Sorry, not the chain rule. We've just done the product rule. So we're going to substitute that back into this little formula here. And so we have d over dx of x times e to the 3x is equal to a prime b, which is 1 times e to the 3x, plus b prime a, which is equal to 3 times e to the 3x times x. So we have 3x times e to the 3x. And by doing so, we see that the left-hand side of the equation, which is dy over dx, we just proved that that is equal to e to the 3x plus 3 times x times e to the 3x, which is identical to the right-hand side of the equation, which is the exact same thing. So we just basically proven the base case. Now I'll move on to the next slide, where we want to do the inductive hypothesis, which is really simple, right? We're just going to state assume truth for n is equal to k. All right, and then for our inductive step, what we want to say is that we want to prove that prove truth for n is equal to k plus 1. And again, all these two steps are saying is that, hey, if we know that some given number k satisfies the expression that we're seeking to prove, then we know that we want to prove that the number k plus 1 will 100% for sure also satisfy the given equation. All right. Okay, so how do we do this? let's take a look at our second tip, which basically asks us to wonder what's really happening as we go from n is equal to k to n is equal to k plus 1. So when n is equal to k, I'll write it down here. What we can do is we can go into our original equation. Our original equation is this one, of course. And what we can do is we can substitute k as n. And we're just left with the equation d to the k, it's not d to the k, sorry. The kth derivative of y with respect to x is equal to nothing but k times 3 to the k minus 1 times e to the 3x plus x times 3 to the k times e to the 3x. Remember, now all I just did was I substituted all the n's for k's. That's really simple. And when n is equal to k plus 1, we want to prove that the following equation is true. So we want to prove, and this is we assume, then we want to prove, again, we go back to our original equation, which is of course this one right here. What we do is we substitute all the n's for k plus 1's. So doing that will end up giving us the following equation that we need to prove. So the k plus 1th derivative of y, that's very trippy to say, with respect to x, is equal to k plus 1 times 3 to the k times e to the 3x plus x times 3 to the k plus 1 times e to the 3x. Perfect. So now let's ask ourselves, what really happens as we go from the first equation to the second equation? Well, we're just differentiating y in terms of x one more time, right? So as you see in the first equation, we're taking the nth derivative, we're taking the kth derivative of y in terms of x. And in the second equation on the left-hand side, we see that we're taking the k plus 1th derivative of y with respect to x. So all we're doing is we're differentiating one extra time to go from the case of n is equal to k to the case of n is equal to k plus 1. Cool. So now that we've figured out what's actually happening as we go from n is equal to k to n is equal to k plus 1, we can begin to apply tip 1, which basically says to write the equation you get from the inductive step. Remember, that's the n is equal to k plus 1 equation, in terms of the expression from your inductive hypothesis. Remember, that's the n is equal to k expression. Now, what exactly do I mean by these expressions? Well, I'm just talking about these guys over here. I'm talking about this guy and this guy. And what we want to do is we want to write this guy in terms of this guy, which is all right. So how do we do that? As we just discussed, we can do this by differentiating the guy at the top, this guy, an extra time, right? So if we differentiate this an extra time with respect to x, we actually get the second expression over here. So what I can do is I can take the left-hand side of the equation we want to prove, and I can write it in terms of this expression over here. And again, we do that just by differentiating it an extra time. All right, now what do we do? Well, as you see, this thing looks super familiar, right? We assumed that this thing, which is that thing, is equal to this. So we can just plug that in, right? We can make that substitution. So this is equal to nothing but the derivative with respect to x of k times 3 to the k minus 1 e to the x plus x times 3 to the k times e to the 3x. Right, we just made that really quick substitution. And now it all becomes clear. Now we see exactly what we have to do. We see the finish line and how we get there. We just need to take this expression's derivative with respect to x. All right, so how do we do that? It's the final step, and let's do this derivative really quickly. So how do we take this derivative? Well, let's separate the two terms. Let's first take the derivative of the first term. I'll say first term, term 1. I'll say term 1. And then we'll take the derivative of the second term, which is this guy over here. So this is the first term, this is the second term. Okay, so what's the derivative of this term? Well, we are doing the derivative with respect to x, so all the k's are just constants. So really the only thing we are differentiating here is e to the 3x. So we have, this is nothing but, we're just going to treat k times 3 to the k minus 1 as a constant. I'm just going to write that as an aside here. And the derivative of e to the 3x. As we've already established earlier, we've seen this derivative. This is just equal to 3 times e to the 3x. So we're just left with k times 3 to the k minus 1 times 3 times e to the 3x. We can combine these two to get k times 3 to the k, right? Because 3 to the k minus 1 times 3 is 3 to the k, times e to the 3x. Boom, we just did that. Okay, term number 2, we're taking the derivative with respect to x of x times 3 to the k times e to the 3x. All right, now this one's a little bit trickier, and it seems that we have to apply the product rule here, right? So what we can do is we can rewrite the product rule. And we can make the following substitution. We can say that a is equal to 3 times 3 to the k times x, which is this guy. We can say that b is equal to e to the 3x, which is this guy. Then we can differentiate these two. So a prime is equal to the derivative of 3 to the k times x. 3 to the k again is a constant, and the derivative of x is 1, so we're just left with 3 to the k. And b prime is, as we saw twice before now, is just equal to 3 times e to the 3x. So a prime b, what's a prime b? That's 3 to the k times e to the 3x, which is nothing but 3 to the k times e to the 3x, of course. And b prime a is equal to 3 times e to the 3x times 3 to the k times x. 3 times e to the 3x times 3 to the k times x. And as you can see, what we can do is we can combine this k, the 3 and the 3 to the k to get 3 to the k plus 1. So let me just erase that, and I'll just write in 3 to the k plus 1. Cool. Now adding these two together, what we get is, maybe I'll write this on a separate page. So we have k times 3 to the k, k times 3 to the k times e to the 3x. I'll have e to the 3x plus 3 to the k times e to the 3x, 3 to the k times e to the 3x plus 3 to the k plus 1 times e to the 3x, k to the e to 3 to the k plus 1 times k times e to the, it's really testing my memory right now. Okay, so we've just proven that this is equal to d k plus 1 y over dx k plus 1. All right, and what is the expression that we want this to be equal? What is the expression that we want to prove this to be equal? Well, the expression that we wanted to originally prove this to be equal is we wanted to prove that we want to prove that this guy is equal to k plus 1 times 3 to the k times e to the 3x plus x times 3 to the k plus 1 times e to the 3x. sorry, e to the, yeah, e to the 3x. So now we're really close, and we notice that, hey, let's take a look at these first two terms of our equation. The first two terms of the equation that we've got to. And we notice that we can factor out of 3 to the k times e to the 3x. So we're just going to factor that out. And what are we left with? Well, in the first term, we're left with k. In the second term, we're left with 1. And then we're just left with 3 to the k plus 1 times k times e to the 3x. Sorry, this isn't a k. This is an x. Let me just make sure. Yeah, this is an x. That's my bad. That is a typo. And we see that, hey, these two are identical, right? Other than these two being swapped around, but that doesn't matter. We can just swap these two around, and we can say that, hey, we've just proven that the k plus 1th derivative of y with respect to x is equal to this expression right here. And therefore, the left-hand side, which is this guy, which is initially this guy, is equal to this guy, which is the right-hand side, right? And we can see that in our original equation. We just proved that this guy is equal to this guy. Therefore, our inductive step is done, and our induction is therefore complete. So that took a little while, but I hope this gave you a bit of intuition and this all made sense. And we'll do one more problem of this type in the next video that deals with a bit of trigonometry.